In 2021 alone, the global semiconductor industry shipped 1.15 trillion chips. That is roughly 145 chips for every person on Earth, powering our phones, our cars, and our computers. Yet every single one of those hyper-advanced devices begins as one of the most ordinary, abundant materials on the planet: sand. Taking a scoop of beach sand and turning it into an electronic brain that performs trillions of operations a second takes about 3 months of microscopic engineering. This photograph shows the environment required for that process. Inside hyper-controlled cleanrooms, workers in protective suits operate under specific yellow lighting to prevent particle contamination. To understand exactly how this works, we have to step onto the factory floor and follow the physical assembly line, step by step, from raw material to finished product. Grasping this precise sequence of physical transformations is the only way to understand how a piece of geology becomes the engine for a modern device. First, the silicon is purified from the sand. It is melted down and pulled into a perfectly structured, 99.99% pure cylindrical crystal called an ingot. As we can see in this technical illustration, that ingot is then sliced into completely smooth flat discs called wafers. These canvases are typically 300 millimeters wide and about 1 millimeter thick. This image illustrates the next phase. On the far left, a base layer is deposited and covered with light-sensitive photoresist. Moving to the center, extreme ultraviolet light is projected through a stencil-like mask, reducing a pattern and exposing the photoresist below. When that light hits the resist, it triggers a chemical change. The exposed areas harden, printing a complex blueprint directly onto the surface. The optical system shrinks these patterns until the final features are thousands of times smaller than a single grain of sand, small enough that billions of them can fit onto a surface the size of a thumbnail. Because the wavelength of this light determines the smallest possible feature size, photolithography sets the physical speed limit for the entire industry. It is the step that dictates exactly how many transistors can be packed into a single square millimeter. With the blueprint printed, the factory transitions from drawing to physical sculpting, a process known as etching. Using chemical baths or plasma gases, the soft, unexposed resist is washed away. This carves microscopic, three-dimensional channels directly into the silicon. Next comes doping, or ion implantation. Because raw silicon isn't a perfect conductor or insulator, it's bombarded with positive and negative particles to alter its electrical properties. Directing these ions into specific areas creates transistors, the fundamental electrical switches that make the chip function. That complete 4-step cycle, deposition, lithography, etching, and doping, is then repeated over and over and over again. Dozens to hundreds of these layers are stacked sequentially on top of each other, creating dense, three-dimensional architectural blocks. This repetitive sculpting is exactly what transforms an inert piece of rock into an active electronic brain capable of holding billions of switching transistors. Before leaving the factory, the layered wafer undergoes rigorous final quality control. On the left, a multi-point test probe evaluates the grid of circuits in milliseconds. These automated probes check for correct responses, immediately identifying and discarding any faulty or dead circuits. Next comes the physical extraction. This photograph shows a single silicon wafer cut into hundreds of individual square chips, known as dies. During assembly, these functional dies are mounted to a lead frame. Microscopic metal wires are connected to the chip, allowing it to route external electrical signals in and out of the system. Finally, we reach the packaging stage, shown in this exploded view. A heat spreader is attached to keep the chip cool, and the entire assembly is sealed in a protective case to survive the real world. This grueling, months-long microscopic assembly line happens millions of times every single day in order to satisfy the massive global demand. It relies on a massive, highly coordinated international ecosystem, from American circuit design to Dutch optical lenses to Asian fabrication facilities. Every digital convenience we rely upon is the direct result of humanity's ability to continuously engineer and mass-produce this microscopic architecture.